Consider this word problem. How much energy is needed to heat a swimming pool that contains 162 cubic meters of water? Currently at 15 degrees Celsius, and we want to heat it to 27 degrees Celsius. And we have some information here given to us. Well, the first thing we do, let's draw a picture of this. So we have a swimming pool. I'm going to simply draw a rectangular swimming pool. It really doesn't matter. It can be any shape at all, as long as it contains 162 cubic meters of water. So we'll consider this an outdoor swimming pool, and it's filled with water. And the volume here is given to us as 162. And it's going to be heated. And I'm going to draw in some electric heating. This is obviously not how a swimming pool is going to be heated, but for our purposes, I'll drop in some electric coils right here. And we're going to heat up the water using these electric coils. And we're going to make the assumption that this is completely sealed. For our equations, this is completely sealed. And as we heat it up, there is no heat loss. Of course, in real life, when you heat up water and you pour it in, you're going to lose some heat. But in our instance right here, for the purpose of this equation, or this solution, we're no heat loss. No heat loss. And the equation we're going to use for this, it comes from our equation sheet. And we're interested in this one, where Q is heat energy, equals Cm delta T. And if we have a look at our key topic sheet, here's our equation for temperature and heat 2. Here's our equation. And there's a special graph chart here, which we're going to use. The details of all of this is written here in this key topic sheet. And we're interested in this chart. So we have temperature versus time. I'm going to reproduce this chart on our word solution. I'll just reproduce it here. There's temperature, and here is time. And the two temperatures of importance are the freezing temperature of water and the boiling temperature of water in degrees Celsius. In degrees Celsius, this is time. So if we had some ice at some low temperature, ice is going to heat up, then it's going to hold temperature as it does at a phase change. And everything I'm saying now is explained here in this sheet. And then it's going to start to climb again until it hits the boiling point. Going to hold yet again and continue. So using this chart, and this particular equation right here applies to this part of the chart. That equation applies to this portion of the chart. And we're given two temperatures, 15 and 27. So here is 0, so we'll call this, say, 15 degrees Celsius as we go across to make that 15. And this is obviously not to scale, and we'll go to 27. So it's within that slope. Having said that, let's have a look at our equation, or let's have a look at what is given to us. Well, let me backtrack again. We'll go back to our equation. This delta T here needs to be opened up a little bit. This is heat energy. How much heat energy, or how much energy, this is it right here, Q, is what we're looking for, is equal to C. C is a constant. And if we look at our equation or formula sheet, there are various values for C, like specific heat capacities. This is one specific heat capacity for ice, up to 0 degrees Celsius. For water, which is the range that we are working in, liquid water, C has a value of 4186 joules per kilogram Celsius degree. And if we were interested in the steam This will be the value for C. So that's what we're interested in right here, this one. So we know what C is. M represents mass. And this is the mass of all of this water. We're given to us in volume, so we just have to change that volume into mass. We have some conversion factors given to us here. And delta T, well, this is temperature final minus temperature initial. So we know our final temperature is going to be 27. Our initial temperature is 15. We can put that in here. So let's make a quick list here of what we are given. Q is what we want to find. C is given to us, well, we just take it directly from our charts right here, 4186. And the units for that is joules per kilogram Celsius degree. Mass, well, we need to calculate the mass. I'll do that momentarily. And the two temperatures, temperature final, temperature initial. Temperature final is 27 degrees Celsius. Temperature initial, I'll make that capital T, is 15 degrees Celsius. And we need mass. And that's just a matter of converting this into mass using these conversion factors here. So let's do that. Mass. We're going to change 162 cubic meters into kilograms. And here is kilograms. And we have some conversion factors. So let's change cubic meters into cubic centimeters. I'm going to take a shortcut on this one. Centimeters cubed is equal to 1 cubic meter times 1 liter is to 1,000 cubic centimeters times 1 kilogram is to 1 liter. Doing the multiplications, canceling out the units, cubic centimeters, cubic centimeters, cubic meters, cubic meters, giving us liters and liters. Effectively changing this into kilograms, and it's 162,000 kilograms for fresh water. So now we have the mass. All that's left to do is to take this information and put it into our equation. So let's do that now. Here was our equation just one more time. Q is equal to Cm, temperature final minus temperature initial. Putting in the numbers for heat energy is what we're looking for, letter Q. 4186 joules per kilogram Celsius degree times the mass. We said that was 162,000 kilograms. Times the two temperatures, 27 minus the 15. And when we do a subtraction of degrees Celsius, the unit changes to Celsius degree. Looking at the units, Celsius degree cancel out, Celsius degree cancel out, kilograms and kilograms cancel out, leaving us with the unit of joule. And all energy, because this is heat energy, all energy has a unit of joules. Doing the calculations, heat energy, Q, is equal to 137, 584, 123 joules. That's a lot of joules. Reducing this to proper significant figures, and for our purposes, I'm going to ignore temperatures for sig figs. And we'll just use the volume of the fluid, which is 3 sig figs here, 162 cubic meters of the water. And that's just my preference to ignore the temperatures. Go to 3 sig figs, approximately 8.1123. Look at that fourth one. So this is going to go up by 1. It goes up 1. Got a decimal point here and a decimal point back here. It goes 1, 2, 3, 4, 5, 6, 7, 8, 9. 10 to the power of 9 joules.